I just put a crash, it's only giving one now.
From 4x speed to 0x speed. It averages 2x speed. All right, so we've seen this diagram before from the last one, and it happens to be exactly how I start this sequence of, what is it, 94 slides? It's quite a few. There's a lot to cover here and a lot of material that if you take this material and apply it, there are very few instances where it doesn't perform very well. So let's start with refreshing ourselves on agent environment interactions. Hopefully remember this a little bit from before. So we have our AI and or us, if we're considering us to be an agent. If we do that, then at any particular discrete time step t, we take some action. That action affects the environment in some capacity. As that environment changes, we perceive a change in the state. And we also receive some kind of reward from that process. How we define that reward, we'll talk about in a bit, because that is something that we, the programmers, have power over. If we're going to train an agent to reach an intelligent outcome, we need to design the reward function in a way that aids the learning process of the agent. So that's just a process that goes on at every discrete time interval until the end of time. And or it's continuous and we just discretize it ourselves as we say, at every 5-second interval, we're going to make a decision about what we're going to do. Perceive the change in reward between the last time we did this and the current. But there are also continuous episodes that will show how to get rewards for as well. First thing we should talk about are MDPs. Who has heard of a Markov decision process before?
I don't even know who that is.
Markov, famous mathematician. Yeah.
Oh.
Markov.
So a Markov decision process is, especially for those of you who are in compilers, this will link to something that you've seen before as well. So there are states that we're going to think of as graph nodes. There are actions that are the transitions between those states, and then there are rewards that for each transition you can calculate the associated reward of transitioning from state to state. But what makes it a Markov decision process is that we don't store a history. And if we don't store a history, that means that when we're in a particular state, it doesn't matter how we got to that state is just where we are. For those of you in compilers, it's very much like regular languages and finite state machines, because we don't need additional memory. However, in a Markov decision process, we don't necessarily guarantee a particular transition. There may be multiple possible transitions out of a particular state with an associated probability of taking that path. So we have to define some transition probabilities. Let's say we're an agent, we're in a particular state. There are some number of successor states to this based on the actions that you take. When this agent is in this state, as I'm cranking through the options and thinking, what action should I pick, such that the state that I end up in and the reward that I receive you're maximizing that reward from this current state's perspective. You should take the action that maximizes the expected reward of wherever it is that you end up. However, when you take an action, probabilistically, we may end up in different states. It's something like you're playing chess. You make a decision about which piece to move and where. You don't know what state you're going to be in when it becomes your turn again, because the opponent has to move with respect to whatever the opponent can do. You may be able to define some transition probabilities. I think my opponent is most likely to play this, but they might play this, and they might play this, and they might play this. Maybe 80% of the time, I think they're going to respond in this way. 10% they're going to respond in this way. 10% they're going to respond in this way. If you could have an estimate for that, then you could come up with an expected value of making that move. There are 3 possible successor states after the opponent has moved that I think are reasonably likely. So I want to make the move that maximizes my chance to win after my opponent plays based on the move that I make, if that makes sense. Also note, though, that chess is very much like a Markov decision process. It doesn't matter the order in which you got to that particular chess state. When you're there, you're there. all games in that state are equivalent at that point. Even if maybe white was winning and now it's a draw, maybe black was winning and now it's a draw, doesn't matter if you got to exactly that same state, how you got there. How you proceed from there doesn't matter on that hit, doesn't depend on that history. So let's actually look at how we could define what that reward should be. So this stands for the probability that we end up in a particular successor state and receive a particular reward, given that we were in this state and took this action. So it's something like, all right, I'm in a particular chess state, I'm gonna move my knight from this state to that state. What is the probability that I end up in a particular successor state when it becomes my turn again, based on what the end user did and the reward associated with that? So maybe I think there's a small chance that my opponent falls for my trap. Maybe this is the goal of this, is to set up a trap. With some probability, they're gonna fall into that trap and I'm gonna get a massive reward for goading them into that trap. On the other hand, if they're intelligent and see the trap coming, they can escape from the trap in a way that is bad for me. So we just define each possible successor state and reward that you get if you end up in that successor state based on the state that we were in and the action that we took. This would be the snapshot of the chessboard right now. The action being, I'm going to move the knight from here to there. What's the probability if they fall for the trap and I get a high reward, or they don't fall for the trap and I get a low reward? So defining that probability is defined as the probability that, given that we're in a state, we're going to say the following state is S prime. The reward is S, given that at time t minus 1, we were in state S, and at time t, we took that particular action. So equivalent ideas. We just need to have some way of defining that probability. That would tell us the expected value of taking this action from this state. Does that make sense? If they fall for the trap, my chance of winning goes up. If they don't fall for the trap, maybe my chance of winning stays the same. Maybe my chance of winning goes down. But if I can estimate the associated probability that they're going to fall for that trap, I can figure out the expected value of setting up that trap. From this allows us to make deductive arguments about what kinds of actions we should be doing. So the probability that we end up in that new state, given that we were in a starting state and took a particular action, we just say, okay, what is the probability that at time t we're in this state S prime, given that at time t minus 1 we were in that state? So what is the probability that we end up in the trap was successful, given that we were in position to set up the trap? What is the probability that we were unsuccessful with the trap, given that we were in a situation where we could set up the trap? So it ends up just being the sum of all rewards. You multiply the probabilities of ending up in those successive states and the rewards that you get. So let's say we can set up some kind of basic system here, where here is the state of the chess board that we are currently in. We can imagine there's two successor states from this. This is the trap was successful, and this is the trap was unsuccessful. We could say, if we knew the probability of this, let's say we know our opponent, they're pretty gullible. Maybe 3/4 of the time the trap is successful, and 1/4 of the time the trap is not successful. When we end up in the trap, let's say right now we have a 50% chance to win. If we go into the trap, maybe now there's a 70% chance to win. And now we're at a, maybe we lose 5% if they don't fall for the trap. We're not setting ourselves up for failure, but maybe they have a way of working around the trap in a way that gives them a slight advantage. If we wanted to calculate the value of being in this state and choosing this action that moves to set this up, we could just take the sum of the change in the probability. So the reward of being here would be 0.2, and the reward of being here would be negative 0.05. The change in probability of winning from moving from one state to another state. So the value of this action, if we wanted to figure that out, we just multiply the probability of ending up in that state times the change in reward that we would get if we reached that. So we would just set this up as 0.75 times 0.2 plus 0.25 times negative 0.05. And that would give us some small positive value as the reward, the expected reward of doing this. You can just sum up all of the rewards that you get from all of the possible successor states that we could end up in. So these are the possible successor states that we could end up in. Here was the state that we came from, so using this would be S. These would be potential S primes. The action that we take is that this is just one action. With that one action, we can end up in multiple different states, probabilistically. So this is the equivalent of looking at, given a state action pair, we're going to use this terminology a lot, this concept of a state action pair. We're in a state, we choose an action, what is the value of taking that action from being in that state? And we can define that as this expression. Questions on that? Does that make sense?
So the equation, like, before you throw it in the integral, it's just describing that situation of the probability of ending up in each state.
Yeah, and the change in value of ending up. What is the reward that you get if your opponent is goable? What is the reward that you get if your opponent is not goable? And rewards can be negative. So if they don't fall for the trap, maybe your chance to win goes down.
And that can be more than two, right?
Right. Yeah. This would just be, they fall for the trap or they don't fall for the trap. In chess, what are all of the possible actions that your opponent could make? What do you think is the associated probability that they would make any of those 30 possible actions? How good is that for you? So it becomes really complex really quickly. But it at least gives us a way to talk about this kind of environment in a way that would allow something like a chess AI agent to make an intelligent decision. This makes some vital assumptions. We know the environment, we know the associated probabilities for this, and we know the associated rewards. That's a lot of information that we're assuming that we have. Can we imagine that every learning environment has all of that information public? Or is something that we could learn? The first thing we're going to talk about is how to learn these values. And the second thing we're going to talk about is if it's impossible to learn these values, what can we do about it? So I'm going to try to do that. Whenever there's math on the screen, I'm going to try to draw it so you know what all the variables represent, give you an example of something. If I'm not doing that to do something at that level that makes sense to you, let me know and I can go into more detail. I've used the chess example, but we're going to use a much simpler example to dive into this idea. So we have a robot. This robot has a battery level. It's either high or low. It can now take actions that either search for dirty places to clean, wait, do nothing, or move to recharge. So we can define a Markov decision process for this and a reward function for this in a way that says, here are all of the possible states, actions, and states that you end up if you take that action from the state. The associated probability of ending up in that state, and then the associated reward for being in that state, taking that action, and getting to that successor state. So if the battery is high and the robot decides to search for places to clean, there is some probability alpha that the battery status remains high. The opposite probability, 1 minus alpha, is going to be that the battery moves from being high charge to low charge as it does that search. The reward for doing this is just whatever reward you happen to get from searching. There's some probability that we find something to clean and can clean it. If the battery is low and we search, what happens? There's some probability beta that the battery happens to be high at the end of that. Probably pretty. Oh, sorry, if the battery is depleted because of this, this means the battery was depleted. So the probability that if it's low and you search, there's some probability that the battery status, basically the end user has to go find the dead robot, go plug it in. So the reward for this is going to be -3 that says that the user had to intervene and go rescue you from your own incompetence. On the other hand, if you're low and you choose to search, it's not guaranteed that you're going to fail. You may just stay low, and in that case, you get the reward for searching. Because you're still searching, you still have the opportunity to go charge yourself before you die. On the other hand, if you choose to wait, that consumes no battery, so with probability 1, your battery remains charged. With probability 0, it becomes low, so that will never happen. On the other hand, if you wait and the battery is low, there's no way for the battery to charge itself without being charged, and it's guaranteed to stay low. On the other hand, you get a reward that is the reward of waiting, whatever that is defined to be. We're assuming that some of these are going to be, or all of these are going to be filled in by some end user to customize the behavior that should be learned. For instance, if the probability of beta that gives you that reward of -3 is 0, there is no way for this recycling robot to have its battery die. In which case, we don't need to consider it. But if that probability is really high, then there becomes a very probabilistic high chance that you're going to get this -3 reward. Depends on the value of searching at that point, whether it thinks it should go recharge itself or not. So if you go recharge yourself, you certainly, with probability 1, go from low battery to high battery, and you just get no reward for that because you're not cleaning anything, you're recharging. If your battery is low and you recharge, there's no probability that your battery stays low. You will recharge, and you again get reward 0, showing that yes, you didn't clean anything, but also you're preparing yourself to be more effective at cleaning in the future. That reward for cleaning in the future will back propagate to the fact that you didn't die, you didn't get this -3, you didn't deplete your battery, so you can now continue to be effective. So a setup like this creates a learnable environment. If we filled this all out with values, then there would be an optimal set of actions at any particular state for the recycling robot to do. And you could analyze that to figure out, based on some Markov decision process that this defines, basically it ends up looking kind of like this. There are 2 states to this, battery is high and battery is low. Then you make some number of actions. You can choose between, if your battery is high, you could wait, you could search. And if you wait, we know exactly what's going to happen. If you search with some probability alpha, you go back to high battery, and with some probability 1 minus alpha, we go to low battery. So we can see now how we have a state machine, for those of you who are in compilers, that allows you to determine with some probabilistic movement where you're going to end up. If you could analyze this 1 step into the future, 2 steps into the future, 3 steps into the future, you could start to get an approximation for some policy that this robot could take that would maximize its expected reward over time. We're going to talk about exactly how to do that. Questions on this example, or setting this up as kind of a state machine or a transition graph?
I haven't taken compilers, so I don't know what the state machine is.
It just means that you have some states, you have some transitions between states, and at the end of that, you have some kind of, for compilers, you end up in a final state or a non-final state to tell you whether you accept or reject. In this case, this is an infinitely running state machine that we want to figure out what is the value of being in a high battery search. Because we know that, we don't know for sure that we're going to come back here, but we make the decision to search without knowing where we're going to end up this particular time. But by analyzing the environment, we can come up with some approximation for the value of being in a high battery state and searching. Yeah,
I'm assuming that high is the initial state.
I would assume so as well. Yeah, you're going to charge, you manually charge the robot. And then you say, go do your thing. Don't die. Don't make me intervene. Please just clean my house. When I come home, I want to see a clean house, not a 10% clean house and a dead robot. But depending on how we train this, the rewards that we generate from this, it will either be successful at that or unsuccessful at how it can learn. So we need to design a reward function, and then we have to design what it means, what it looks like to learn based on that reward function, so that it can, via the experience that it gets, train itself to not die. Train itself to clean efficiently or effectively. So how do we design those rewards? The idea is that there's some amount of time that this robot is going to clean, and we want it to be able to say at the end of that time, we want to maximize the cumulative rewards that it has accrued. So, how do we design rewards where it is learnable to do whatever it is that you want your agent to do? For a maze, you can imagine that we have a starting position and an ending position. Doesn't really matter which one is which, but you want this robot to figure out how to effectively navigate from here to here. A good reward function is that you will give it a -1 reward for every action that it takes. That way, if it takes longer to get to the finish line, that run scores lower than if it more effectively or efficiently goes from the start to the end. And that way it can learn which runs are better than which other runs based on the decisions that it made. So maybe this robot starts and then it immediately turns right the first time. And it circles around in here for a while, comes up here, and eventually by happenstance finds the exit. And maybe it gets -216 from that first run because it took 216 discrete time steps for it to navigate. Maybe the next time it doesn't turn right and instead turns left, and it happens upon a way of getting there faster, and it gets a score of -102. We have some way of saying now that that second run was better than that first run because the reward was higher. So there is some aspects of that first run that performed worse. Was that decision of turning right immediately partially responsible for that lower score that it got? Once it did this, when it turned left here instead of right here, was that partially responsible for the score that it got? You can imagine that a robot doing this 10,000, 20,000, a million times would start to be able to correlate runs that ended poorly with decisions that it made. In all runs where I scored worse than -200, I turned right as the first action that I did, or in 90% of them. Or you start to you understand that the correlation of these ideas lead to the causation of your low runs. So you learn to not do that. Eventually, you would assume that something is able to figure out what that minimum path is, just from straight up brute force, from learning that. Depending on the complexity of the task, that can take a while. Reinforcement learning agents tend to be really stupid for a very long time initially, until they find something that they happen into something that is a slight improvement. Then they can start learning. So we actually want to nudge the agent in the right direction to whatever extent we can. You can imagine the state space of the distance that this has to go. If we say the very first thing you should do is go forward and then turn left. If we just stated that much as a good start to this process, it has less to learn about how to get to the final state. So that was kind of the maze example. If we have some kind of rover and we want to get from the current location of that rover to some destination that's in front of it, then we give it a reward as it moves forward. How far away are you from the goal? Give it some kind of reward that's based on when it gets closer to the goal, you're going to reward it when it moves toward it, and you're going to penalize it when it moves sideways or away from it in some capacity. So it would very quickly learn to get from here to there, I just need to go straight. To get from here to there, I need to turn and then go straight. Or some kind of agent that is maybe in an Amazon warehouse that is trying to make sure that boxes get stored where they belong. Then we want to give it +1 for each box. And then at the end of each day, maybe it sums up the cumulative reward that it got for the day about how efficient it was, how many boxes was it able to move from point A to point B. And then it will learn how to maximize the value of the trajectory that it uses to minimize the amount of time that it takes to move those boxes. It's not something that we have to hard code, as long as we're okay with it learning. I shouldn't drop the box. How does it learn that it shouldn't drop the box? By dropping the box. We'll first look at episodic tasks. So these are tasks that can be broken down into episodes. This means that eventually this process terminates and gets restarted. An example of this is tic-tac-toe. We can play this game tens of thousands of times. Each episode is from the start of a game to the end of the game. For the maze, when you reach the destination, the exit to the maze, then it gets some reward and restarts. So each episode is independent. The process that it took in the previous game or the previous maze is not relevant to its score in the current episode. If you lost the last tic-tac-toe game, you don't start at a disadvantage because you lost. You start at exactly the same point you did before. When you start the maze over, it doesn't matter if it took you 10 billion steps to get to the exit. You still have the ability to do the optimal actions to get there as fast as possible. But we end in some kind of terminal state that ends the episode. So in tic-tac-toe, the game ends. In the maze, we reach the exit. So how do we determine what we should figure out for the reward for a particular episode? We know that each time step, the agent is getting some kind of reward. Like we said, for the maze, it was always going to get something like -1 for each turn, for each move forward that it makes. Every action that it takes has an associated -1. But how do we score an entire episode? How do we score an entire game of tic-tac-toe? More math. It really is just the sum of the reward that you get at every time step. So we're going to call this capital G, the sum of rewards for a particular episode. So we want to say, all right, what is the reward for being where it is? Well, we're going to say the reward at time t+1, t+2, up to the terminating time. We're just going to sum from here to the end, what we anticipate being the end of the episode. What is the reward that we get for that time step? So if we could look ahead and say, how far do we have until the termination of the episode? That would give us an approximation for what our current score is. If we make bad decisions and maybe go in a loop and get back to where we started, we're still just as far from the end goal as we were when we started, but we've accrued some negative reward as we did that. That tells the agent, don't do that. On the other hand, we could have some continuous tasks. So something like the stock market or trading. This happens in real time. We can't easily break this down into the end of episodes. Maybe we could with something like, what is the value of your portfolio at the end of each day? But you could also think of this as just a, from start onwards, maximize the amount of money in my portfolio. So how do we come up with a value, a return, for when we're looking into the future, what is the expected value of the future? How good is it to be in this particular position? We need some way of determining that. So to figure that out, we need to introduce this concept of a discount factor, which we're going to call gamma. Has anyone seen the concept of a discount factor from some class that they've been in? Probably economics.
I took economics 3 years ago, I don't remember.
Excellent. So we talked about this a little bit last week when I talked about this concept of I'm going to give you $5 today or $5 in 60 years. Which one do you choose? That's the concept of a discount factor. If there's some natural probability, let's just say it's one in a million, that any particular day you die on that day. Some really small probability. How would you calculate your chance of being alive in 1 year? Or 2 years? Or 5 years? You would need to multiply those probabilities together to figure out, all right, the chance that I die either today or tomorrow, what is the chance that I'm around for that? Except that we're going to discount the rewards by now multiplying it by something between 0 and 1 that says this is the rate of exponential decay on the value of future rewards. So if this value 0, if this gamma value is 0, it says that $5 today is equivalent to $5 in 10,000 years. Doesn't matter when I receive it, as long as I receive it. A discount factor of 1, sorry, that's 1. 1 says it doesn't matter. 0 says it's the concept of today is the only day that matters. You live once, you might not be alive tomorrow, so maximize like you're going to die by tomorrow. So that's a gamma of 0. Whatever happens in the future, you multiply anything by 0, it goes away. All we care about is the next reward we're gonna get. So this is does not look into the future, is immediately relevant to today and today only. If this is 1, then we're going to treat all of the future like it's exactly as relevant as today, tomorrow. Anything between 0 and 1 becomes an exponential rate of decay. So if you have 0.99, if you got $5 tomorrow, it would be 99% as valuable as $5 today. If you got $5 in 2 days, it would be 0.99 squared times the value of the $5 if I gave it to you today. So it becomes that exponential, the rate of that exponential decay for how valuable is it to receive that reward in the future. Does it make sense why that might be something that is relevant in something like a continuous task like analyzing the stock market? Because there is rate of inflation, you just build inflation into this discount rate, this discount factor. And now if you can get some number of gains in a year instead of today, we're going to discount that by the value of what is that going to be worth in terms of present day dollars. We need to have some level of exponential decay between the amount of time it's going to take from today to the future in order to represent the present value of that money. It's the same reason why if your parents bought a house for $100,000 back in the day, you actually have to use inflation to calculate what the present day value of that is, and it's still cheaper than what a house costs today. But you need to go through that process to be able to make that comparison. You can't just make 1980s money equivalent to 2020's money without some kind of conversion. So the conversion is some kind of discount rate that is applied over a cumulative amount of time. Does that make sense? Any questions on the concept of a discount factor, discount rate? What is that rate of exponential decay? Value is close to 0. Really, really, really fast decline. Values close to 1, slower decline. Values that are exactly 1, no decline. Values of 0, it's a cliff. Okay, next concept we need to introduce, the concept of a policy. So in reinforcement learning, a policy is just a sequence of actions that have been learned to be whatever it is that this agent does. So maybe it starts with a random policy that says, I have no information, so I'm just going to act randomly to figure out at least how to terminate the episode. Once you've been training for a long period of time, maybe your policy becomes more intelligent and you've learned the sequences of actions to take to be able to maximize the reward that you get. So a policy is just states to probabilities of selecting particular actions in those states in ways that define, here is an overarching view of this agent's behavior. You can imagine analyzing something like, I'll go back to chess, stockfish in chess. If you give it some state, it'll be able to tell you what the best move is. But it can also tell you probabilistically what move it's going to make based on whether it's going to make an exploratory action to learn or an exploitative action to take advantage of what it thinks it knows. So that would be the policy that is defined for that particular agent. How likely is it to make particular actions from particular states? Once you know that, then you have defined the behavior of the agent.
You get minimalist Wally from.
Yeah. So it's a minimalist wall, what was that, sorry? I got the first out. Yeah, yeah,
Find that image,
yeah,
or is this just AI generated?
yes. So yeah, we just need to be able to, if we have for every possible action in every possible state, we have a function that defines that, that function is that agent's policy. There's nothing that says that that policy is a good policy, it just defines what does this agent do in this setting. It's the tuning of the parameters. What are the parameters of the agent? Defined to be its policy. On the other hand, we need to figure out, given that we're in a particular state and we have defined a particular policy, what is the expected return at the cumulative, at the end of this episode? Or if we have a continuous process, what is the limit as time approaches infinity? Because we're going to get an exponential decay, so we're going to approach some actual return value as we do this infinitely. As we look infinitely far into the future. The limit of that will approach some value because of exponential decay. So we just need to figure out, okay, what is the expected value of pi is going to represent some policy. So the value of a policy is defined to be the expected value of that policy given the return at time t, given that at time t we're in a particular state. Break that down a little bit. So maybe we want to use chess. That's too expensive. Let's use tic-tac-toe. We're close to the end of the game. Let's say we're playing X and it's X's turn, and here is our game. So it's X's turn. If we have learned from this policy to 100% of the time go here, then the value of being in this state is 1. We're going to win the game on the next play. But if our policy said play randomly, rather than we've learned how to win the game from here, there's a 1 in 3 chance that we're going to win the game immediately. There's a 1 in 3 chance that O has the chance to win the game on their next play. There's a 1 in 3 chance that if we go here, O probably still wins the game if they're playing intelligently. So maybe the value of this, if we're selecting a random policy, is 1/3, if we assume that O plays optimally from here. In 1 in 3 moves, we win the game, and in 2 in 3 moves, we set O up to win the game on their next turn. So depending on the policy, we get a different value for being in this state. But we have to look into the future to figure out what that is going to be, because there's no guarantee that we are 1 move away from winning the game. If we are in this state, we're just starting the game. This is a much more complicated function. The expected value of being here will depend on what is the probability that we are going to move here, 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 or here. And everything that we've learned about what is the opponent going to do to put us back in a position where we make the next few moves. So this is a really difficult question to ask, because we have to think about the entire future of playing the game and all of the options that everyone has. But once we get close to the end of the game, then it's not very complicated to look ahead and see that the game is going to end on the next play, no matter what happens. So this just says the expected value of a policy. So the value of being in a particular state. This is saying how good is it to be here. The value of how good is it to be here is going to be the expected value of the policy. And remember that if we have a random policy, this value is different than if we have an intelligent policy. So we have to look at what is the probability that this policy tells us what we're going to do from here. Then we look at the return from the value. So if we win, this return is 1. If we lose, the value is -1, let's say, or 0. Of being in this particular state, at this time. So to figure that out, we just have to sum all future rewards. If it's continuous, we're going to use that discount factor that we talked about. If it's not continuous, then we just sum up all of the potential future moves that could be made and the probabilities of ending up in those particular states. So if we start here, that's a big branch, lots of math to do. Here, not very much math to do.
Huh.
Yeah,
I thought I remember the last time you used, I think that there was an example, it was, taking into account rotations and flips.
yes.
Yeah.
Yeah, so you would want to be able to do that and say that they're equivalent states, but you don't have to. It would just mean that it's a bigger state space to learn. If you want to make this process easier to learn for a particular agent, then you'd want to be able to rotate the board and say this state is the same as that state, which is the same as that state.
In which case there would actually only be 3 possible places you could go.
Right. Other questions on this?
So just a refresher
Yeah.
about the high level logic of what the map is saying. So basically, the expected that the policy we give it at a given state needs to be calculated by running through expected values of all possible states.
Given this policy, yeah. If you can imagine, you're playing randomly. It's gonna look very different than if you're playing intelligently. If you're playing against I guess. I'm sure on the internet somewhere there exists some tic-tac-toe game where you're playing against someone who plays randomly. And someone who plays, or an agent plays randomly, an agent who plays intelligently. You can tell when you're playing against which, because in one case it acts like it has no idea what's going on the other case, you have to play perfectly in order to avoid losing. So the value of being in a particular state will be different depending on whether you're playing the difficult AI or the dumb AI. And the difference between that is the policy that that agent is using to make its decisions. Has it learned what is better, what actions are better than others in particular circumstances? Or has it not?
If you wanted to make two versions of an AI, but wanted to use, the reinforcement learning for both, one that's like easier to beat and one that's not, is there a reasonably good / easy way to do that?
Yes, the amount of time you train it, or you let it train.
Okay,
If you, because the way you have to start this is that you have no idea how to play the game of tic-tac-toe. The agent's gonna have no, imagine you just stop there and say, you have no idea what you're doing. All right, go play a real person.
okay.
Versus you let it train, you let it play out some games to learn that correlation and causation between when I play not in the corner and not in the middle, I lose more frequently than I win. If it can learn that kind of correlation, then it will be much less likely to start the game that way. Which means it will be more likely to tie the game or win the game than if it hasn't learned that. You train that and then you set that agent loose against a person and it will perform better than the one you didn't allow to train at all. So the time that you take to train is proportional to the amount of information that the agent can glean from the experience that it has. So that is a state value function. This says in some Markov decision process, we are in a state. Here's where we are, and we need to figure out, based on all of the actions that we could take from here, how good is it to be here? With some probability, we're going to take this action. With some probability, we're going to take this action. With some probability, we're going to take this action. With some probability, we're going to take this action. So we want to get a value that represents how good is it to be right here in this state. We call that V. This V that we see right here. On the other hand, Q represents an action value function. So instead of a state value function, this is saying we're in this state and we could have picked this action, we could have picked this action, we could have picked this action, but we picked this action. How good is it to have been in this state and picked this action? Because we don't know for sure necessarily where this ends up. If this is probabilistic, this could, with some probability, end up here or end up here. We saw this with the recycling robot example. There was some probability that the battery was drained from high to low and some probability that it stayed high. So we need some way now of showing for the rest of this episode or the rest of time forever, how good was it that we were in this state and picked this action? So it's not the same as looking at all possible actions that we could make and trying to identify a value for this state. We're saying now, how good is it to have picked this particular action in this state? Now look at the rest of the possibility space. So to do that, we're still taking the expected value of the policy, but instead of just saying the state was S, now we've made a decision about which action to take. So we've made a decision about which action to take. How do we do this? We just sum to infinity, because if this is a continuous task, we have to look out forever based on the discount rate for each step in advance that we go. Time 0 means what's happening right now. Time 1 means we're going to discount this once. Time 2 means we're going to discount this twice. Time 3 will discount it 3 times. We're just getting further and further into the future. We want to, at this point, say, what is the reward at that time step, given that we were in this state and we picked this action? So we're simulating into the future, basically, in a way of saying, if we let this play out forever from here, what is the value of being in this state, taking this action based on every possibility from here on out? As you can imagine, the base value of this is brute force and has exponential time complexity. So we're going to have to find some way of improving this and making it actually calculable. Because for any reasonably sized activity, this process will not terminate. We're not going to get an answer back to this value until the sun grows into a red giant and sets the earth on fire. Possibly later than that. So how do we do it? We use the Bellman equation. Anyone seen the Bellman equation in any other class? Anyone who's taken Tony Espinosa's classes has
Never run it,
probably
that's
seen
not-
this in some.
Yeah.
Yeah.
I know that he uses this. I forget what he uses it for, but I know that in some Tony class, I think it's 330. I think in 330 you go over the Bellman equation.
Yeah, sounds
It's
familiar.
330, we use it to map out nodes and networks.
Yeah. So same equation. This is just like nodes and networks. In fact, if you can apply reinforcement learning to some kind of optimization of nodes and networks, some AI that's going to make some decisions about those nodes, their connections, what information is sent and when, how. But in general, the Bellman equation is just a recursive relationship defined between the value of this particular state and the values of the successive states. So what happens if instead of trying to look out into the future and analyze absolutely every possible route that we could make, we recognize we look one step ahead and the value of that state, even if it hasn't fully, what's the word I'm looking for? Converged, that's the word I'm looking for. If the value of that state hasn't converged yet, you're going to take that as an approximation for the value of this state. And then as you get more experience, you will slowly back propagate to the states that you have been in many times to be able to get a sense of now how good is this state. So it's very similar to tic-tac-toe of we know the value of a state really well if we can win the game in one move from this. But a lot of information has to be gleaned to know the value of the very initial state because of the size of the branching factor to all of the different ways that we could win the game or lose the game. If you start with something that is unknown, you will slowly start to back propagate. I won in one step when I was here, which means that when I'm 2 steps away from that, I can put myself 1 step away from winning by making this move. Once I know that, 3 steps away from winning, I can make a decision that leads me to 2 steps away from winning. Back propagate from there, and you slowly get an idea or a sense of the value of being at the start of the game, the value of having made one particular move based on thousands, millions, billions of examples of playing this game. You have a massive sample size of episodes of playing the game, you start to get a better and better sense of the value of a state. So we can use the Bellman equation instead of saying we're going to find the return looking forever into the future or until the episode terminates, and say now we're just going to sum the value of everywhere we could get in a single step from here. What are all of the possible successor states? What are the values of those successor states? We're going to backtrack from there and come up with the value of this state based on the sum of all actions, the value of the policy of taking that action from this state, times all the possible ways that you could get to some successive state. So this is something like, in tic-tac-toe, we are at some particular state, doesn't matter which state it is. These are all of the actions that we could take. So maybe one action is putting an X here, one action is putting an X here, and one action is putting an X here. Who knows? Maybe there's a partially complete, but The idea now is we make that action, but we don't know what the state is going to be like when it is our turn again, because O has to move. If we make this move, then O could move here or here or here or here. So this probabilistically becomes all of the possible successor states of the snapshot of tic-tac-toe when control is returned to you after your opponent's turn. If we wanted to map that probabilistically, we could try to get a sense of what is your opponent likely to do if you make this move. If we've seen that in our history, the opponent has done this 3 times and the opponent has done this 1 time, we could now assign a probability to is probably 75% of the time if I take this action, I end up in this state. 25% of the time, if I take this action, I end up in this state. You could use that to say if we had an estimate for the value of being here or the value of being here, you can now back propagate that to here to be a new estimate. And you don't have to consider everything that happens from this state until the termination of the game. When we terminate the game, when we play, we'll be able to back propagate it once, and then back propagate it again, and then back propagate it again, and then again, and then again, eventually reaching S. So this S value is going to be changing over time as we get more and more and more experience playing from this state. The more experience we get, the more intelligently we can make this action selection decision. How we doing?
Like he's breaking.
Yeah, I was just thinking, I was gonna ask that. So let's take a quick break, come back at 3:10. Let's come back at 3:10, reasonably long break. All right, we're back, and I have a lot on the board since we paused. So to describe what we've done here, for those of you who are focused on something else, that's perfectly fine. We're trying to figure out the value of this state. To do this, we have to use a particular policy. The policy that we've identified for this is a random policy that says that we're going to select these actions with equal probability. When we select that action, the opponent gets a turn and may put us in different positions. I've simplified this as much as possible. If you end up here, you win the game. If you end up here, you lose the game. Win the game, lose the game, win the game, lose the game. Backtracking all of this, we can now find the value of this state by saying, all right, 0.33 times 0.2 times 1, the value of being in this state, plus 0.33 times 0.8 times 0 allows us to now see the value of taking this action and how it's going to end the game. If we take this action, a third of the time we win the game, 2/3 of the time we lose the game. We take this action, half the time we win and half the time we lose. So coming up with the value of each of these, you kind of get the value of this action being 1/15, value of this action being 1/9, the value of this action being 1/6. You sum those up because they have equal weights associated with them, and you get a value that goes in here as the value of being in this state. And it kind of represents at this point, according to the best knowledge that you have, the probability of winning the game from state S. Based on this, this is the S prime for some other decision that was made above this. When you play the next round of tic-tac-toe and you reach this state up here, now you have more information about the value of this state, such that when you take some action and possibly end up in this state, now you can back propagate this information that you gained from here into the value of this state. And that continues to just back propagate as you get more and more experience, to the point where now we can get an estimate for the probability of winning when you start the game based on this particular policy that we have. But you can note that this policy isn't optimal for the rewards that we see. It would be better if we had a policy that selected this route because it generates a higher chance of winning than any other action that we could take. So this is all conditional on the policy that this agent is using. So we need to find some way now of changing the policy based on the values that we see, with the goal of eventually coming up with an optimal policy. An optimal policy for a game of tic-tac-toe for an agent would say, we win the game all the time, or we draw if the opponent plays perfectly. There is no way for us to lose the game because we have an optimal policy that always makes all of the right decisions to maximize the chance of winning the game. In the worst case, we tie. Questions on any of that before we move on? So, as I mentioned, the goal is to derive an optimal policy. Let's say we have some policy. It's not necessarily an optimal policy, but we can say pi star now represents the concept of we have optimized our policy. There is no way to improve this policy to maximize or to better have a chance of winning this game. There can be multiple optimal policies, nothing that says that there is one of them, but there exists an algorithm that allows us to derive an optimal policy given an arbitrary policy. So what can we do? We can show that the value functions of any optimal policy is the same. The optimal value function from a particular state just says we want to now maximize, according to the policy, the value of that policy from that state. This allows us to do something that says if we're in this world and we determined that taking this action led us to states that maximize that probability, instead of considering these other options, we're just going to now go here. If this is better than this or this, why would we even consider either of these options? It would be to get more information. We talked about exploration versus exploitation, but imagine that eventually this converges. We have a very good sense of what it's like, what it means to take these actions, how much value we're going to get from taking these actions. If that had converged and we had enough information to know for sure, or pretty much for sure, we could then say, instead of deciding between these three actions, let's just bias it and always go here. So the value of a state is just the maximum over a policy of the values that any policy could make from that state. Same for action values. If we're in a state and choose an action, we're just going to choose over all possible policies, whatever the maximum value of that state action pair is. So we're just going to define an optimal policy in terms of for all of the infinite policies that you could create, whichever one creates the best possible value for the starting state is the best policy. How would you be able to tell if two different chess AIs, if one's better than the other? Well, you play them against each other a billion times, and whichever one wins more frequently is the better AI. Imagine looking at the all possible chess AIs. Whichever one had the best win rate when paired against the other infinite ones would be the best possible chess AI. We would have optimized that process. To do this, we use the Bellman optimality equation, which is basically what I just showed with regards to drawing on the last Bellman equation. We are now saying if we're trying to figure out the best, the value of a particular state, instead of looking at the probability of going down and finding any successive S primes, we're going to say, well, if we can take these three actions, which one of these three actions leads us to the best successor states for us, probabilistically. So we're going to take the maximum over all of the actions that sums up for each possible state we could get into when we pick that action. So if we take this action, we could either end up here or here. So we need to sum the probabilities of if we take this action, what's the chance we end up here times the value of ending up here? What's the chance we end up here times the value we end up here? If we do that, we get a sense of the value of that action. So we're just going to take the maximum of this action, and this action, given the associated probabilities of ending up in these states and getting the associated rewards for getting there. If we do that, then the best thing that we could do, the optimal policy from the state, is to select the best action. We don't need to probabilistically consider it, you just optimize. If we're trying to optimize for an action value, now the root node, instead of being a state, is a state action pair. It's kind of one of these. We took that action, so basically I'm saying from an opponent's turn, the opponent can put us here or here. If the opponent puts us here, we take the maximum of everything from here. If the opponent puts us here, we take the maximum of everything from here. And this allows us to now see what is the value of taking this action. The probability that we end up in one of these states or each of these states times we now just take the maximum of the values of each of the actions that come from there. So the question is, are we thinking about the values of states or are we thinking about the values of actions? In some situations, you'll really want to think about the values of states. In some, you're really going to want to think about the values of actions. It just depends on the environment that you're in. But we call state analysis V, we call action analysis Q. We look dead inside. We look overwhelmed. What questions do we have, and or just something that this doesn't make sense? That's okay too, but give me a sense of how to proceed. How are we doing on this? How do we feel? And lots of Is there any aspect that doesn't make sense, or is it mostly everything?
Mostly everything.
Mostly everything. Let's see if I can come up with a better example for this. I can go back and take that tower. I think that helps. The value of a state is saying something like, all right, it's your turn. There's a particular board state. Take this snapshot. You haven't decided which action to take yet. But what is the value of being in this state? Well, the value of being in this state is the value of the best action that you can take. What is the best initial action you can take in tic-tac-toe?
Corner.
Starting in a corner?
Yeah.
I like it. That is technically the best opening move. So why would we consider the value of starting here if we know that that sucks? Why would we consider that? If we're trying to build an optimal policy for playing this game, the value of this state should already assume we're going to take the best possible action because it's our turn. Why consider suboptimal moves? So we're going to assume that this is already what's happened. And so now the question is, what is the probability that O moves here or 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 here? If we knew what those probabilities were associated with those rewards, we could figure out what state we were going to end up in when it's our turn again. If O decides to move here, if we're playing optimally, one, we've already won the game, but we end up seeing that we took this action, and then the opponent took this action. And so S prime, this next snapshot where we have control, is here. Backtracking to S, empty board. Which action should we take? The one that maximizes our chance of winning the game. So the value of this state is really just, we don't need to consider every possible other action. We're going to prune the tree to just the branch that leads to the maximum chance of winning the game. Don't consider anything else. If this is going to be optimized, this probability should be 0. This probability should be 0 because this leads to a better result than this or this. Assuming we have enough information to be able to make that decision. Does that make sense? So that's just what this is saying. All of this math is just saying that idea. The optimal value for being in this state, if we could come up with the best approximation for being in this state, all we have to say is look at every possible action we could take, pick the best one. How do we know what the best one is? Well, we sum everywhere we could end up as a successor state after the opponent has moved based on the probability of ending up there. How likely is it that the user puts a circle in that lower left corner that puts us in some state S prime and gives us some reward? If this is optimal and we've fully trained on this, we now know 100% of the time we win the game. If we haven't trained enough, maybe we don't know that yet, but getting in that situation would allow us to get an extra piece of information that if we play well shows that this is a really good state to be in. On the other hand, the other kind of question we could ask is, what is the value of making a particular action? So this question was, what is the value of being in this empty state? The next question we could ask is, all right, what is the value of making this move? We're in this state, but we've already said that we're going to make this move. What is the value of being here at this decision point? We know that the opponent can put us in any one of these S primes. So the opponent could still move here, or here. So we need to consider the reward of every possible place the user could put us, but we've already locked in that we're making this move. Once we get to the opponent moves here, now we say, okay, from this position, we're going to take the maximum of that to get to the next action point, the next decision. We're going to say, all right, well, from here, we already know that the best thing to do is to move here. So we're going to take the maximum action that if the user moves here, we're going to move here. And that gets us to the next action point where we've made a decision, but we're waiting for the user to respond. So it's just a matter of, are we trying to figure out the value of a state or the value of an action? Hopefully that helps a bit. Feeling a little bit better? Maybe. Couple of nods, a bunch of nothings, excellent.
Question, when would we want to state analysis versus action analysis?
It depends on the setup. I think we'll see this when we set up some of the possible examples from here. But in general, if you have a decision point at a state, sometimes it makes more sense to analyze in terms of that. And if you have a decision point after an action has already been declared, sometimes that becomes where the action ends. So where is your decision point? Where does the episode end after? When is the episode done? And you can start to backtrack that information. Does it end in a state or does it end in an action? It's a good thing we've all taken linear algebra, right? So if we want to solve this for the optimal thing to do, then really it's just a linear system. We have the number of states in the system equations. We have the number of states unknowns. So we can use linear algebra to find an optimal policy given the system definition. Unfortunately, most games and systems have such a large branching factor that actually solving this is infeasible. Let's say we have 50 equations and 50 unknowns. How long does it take you to solve that? Now you have 10 million equations and 10 million unknowns. How long does it take you to solve that? As the system scales in size, actually solving this system becomes tediously inefficient. So we also need to know some aspects of our environment. Like, we need to know the entirety of the dynamics of the environment. Like in tic-tac-toe, you know what all of the legal moves are. But let's say I tell you to write a general game playing agent. This says you are going to write an algorithm that takes as input the rules to a game and spits as output the decisions to optimally play that game. You don't know what the game is. You don't know what the rules of the game are until runtime. How would you do that? The idea is you don't know the dynamics of the environment until runtime. And even then, what if you don't know? A real world agent often doesn't have a discrete number of actions that it can take. It has an infinite number of actions that it can take. It doesn't necessarily know when is the episode going to terminate. Something like, for you, the concept of optimizing the amount of happiness that you gain between now and when you die Do you know the dynamics of the environment? Do you know the rewards that you're going to get for all of the actions that you take? There are going to be some actions that you don't know the result of until it ends your life. In which case, you really don't want to take that action, but you don't know until you try it and die, and then you don't get to try again. We need, of course, extreme computational power because of the size of the number of equations and unknowns. And we need it to adhere to this concept of a Markov property because we can't keep track of a history. Or we can't, if we have tic-tac-toe in a way that goes, we have X plays here, then O plays here, then X plays here. Is this equivalent to X plays here, O plays here, really bad. Yeah, the X, the O, and now the X plays here. Are these different tic-tac-toe games?
No.
No, it doesn't matter how we got here. How we proceed from here is exactly the same, right? It doesn't matter that we took a different path to get here. This adheres to the Markov property, meaning that we don't need to store things in order to do that. But you can imagine a game that's played where the exact sequence of the actions that you took does matter, in which case it does not adhere to the Markov property. You can end up in the same state with a different reward because you took a different path to that state. In that case, we don't adhere to the Markov property. We can't use the Bellman equation at all, because it asserts and assumes that it adheres to that Markov property. That we don't need to store the history to know the value of being in this state. It's a necessary component to being able to solve this system. So what happens if we need to approximate? This does solve the equation. If we're able to apply the Bellman equation, the game is solved. Tic-tac-toe is so small that we can solve it by just analyzing it from the beginning. It's not large enough that we run out of computation time. But chess, on the other hand, is so large that we have a very good approximation, but we can't just analyze chess from the beginning and solve it. We can't analyze Go from the beginning and solve it. We need some kind of approximation that says, based on the experience that we have, this is the best that we can assume. All right, so approximation, this just means that if we're going to apply approximation techniques, we don't need to know the entirety of the environment. This would be something like in an RTS, revealing the fog of war. What is out there beyond what you know the map is? We don't know. So we can't make an optimal solution, because if we move past what we know, we stop being able to process what comes next. You move right into some unknown and it's an entire enemy camp. You move right into the unknown and it's the edge of the map. Very different end results. Do we have a way of knowing what the associated probability of that is? There's no way to know. We don't know enough about the environment to know what we don't know. So if there's something that we don't know, we need to use an approximation technique. On the other hand, tic-tac-toe doesn't have any fog of war. We know the rules, we know the board, we know you can't place an X or an O outside of those 9 squares. We know that after X moves, O moves. After O moves, X moves. However, if you're creating a game AI and there is this concept of a fog of war, you cannot use the Bellman optimality equation. You cannot get a sense of everything of the game. If you could, you'd be cheating. Imagine making an AI that didn't have the fog of war associated with an RTS. Is that fair to the player? The player has the fog of war and the AI sees everything. That's how most games design their AI. It's terrible. They then make the AI stupid on purpose with all of that information in a way that still makes it challenging but interesting to you. But from an academic perspective, with regards to how useful is that, it's not another player. It's not making the same kinds of decisions that you are. So because of that, underneath the hood, if you actually go analyze the AI the code of the AI that you're playing against, it's gonna seem ridiculous. It's gonna seem silly. If you use reinforcement learning, on the other hand, you can put the AI in the same position the player is in. And it feels much more fair.
You're saying that we can, if there's a different, if the AI knows everything, then the way to make the game less difficult, you're just making the AI make wrong decisions then?
Yeah, that's basically what actual games do, rather than try to train an agent to play the game effectively. They just start with way more information than you do and act suboptimally. And from the end user's perspective, sometimes you can't tell the difference. Sometimes you really can. So approximation just really is, we can now approximate and use an iterative process now to come up with that optimal equation from experience. So the first way to approximate is via our old favorite dynamic programming. So via dynamic programming, we can kind of spread into two different realms that we're going to talk about over the next couple of weeks. The first one is Monte Carlo, and the second is temporal difference. But let's start by just talking about dynamic programming by itself. To use dynamic programming by itself, we need to have the Bellman optimality equation hold. For Monte Carlo and temporal difference, we can learn it from approximation, which is wonderful. We ready for more math? We're going to need a break before more math.
I have a side and tangent question.
Yeah,
What is Monte Carlo?
Monte Carlo is the concept of when the episode ends, you're going to backtrack what happened through all of the decisions that it made to get to that point, and be able to say something like, this was a really good action. This was a pretty good action. This was a somewhat good action. It starts to, the relevance of the action starts to become fuzzier and fuzzier as you get further and further away from winning the game. But you can backtrack and say, I won this game of tic-tac-toe from this sequence of actions. Let's back propagate the fact that I won back to every state that I visited via and apply the discount factor in reverse to be able to now learn the value of each state from that experience. Yeah. Temporal difference is very similar, except that instead of back propagating all the way through the episode, we're going to back propagate one step or two steps, some finite number of steps, in a way that we'll see the differences between them and when it's necessary to use temporal difference. It's slower to learn, but it learns better.
And a shocking twist you'll never see coming. The Monte Carlo method is in Destiny 2.
Yeah.
I didn't know what the Monte Carlo method was until now.
It's fun how that works. How is it in Destiny 2?
There's a gun called Monte Carlo, and it has a trait called the Monte Carlo method. And it also has another trait called Markov's chain.
Obviously, some nerds were involved in the design and implementation of these weapons, and I love them. Do we want to go into this, or do we want to take a break before we go into this, now that you've seen it? Enough summations for you? We want to be refreshed as we start to talk about policy evaluation.
I mean, I feel like we should take a break every hour. It hasn't quite been an hour.
Well, we only have about 30 minutes left before we bid adieu for the day. So it's a matter of, do we want to try to split the remaining time, break followed by 25 minutes? We want to power through the end of the class. Anyone with a preference?
I say power through.
Power through?
I
Agreement, disagreement?
think we should take a break at 4.
Break it forward to about 4:05 and back the last 15 minutes.
Yep.
do something like that. I can tell by just how much people care about that, how how engaged we are. All right. So. I know, it's terrible. We have a policy. We want to compute this concept of a state value for that. To do that, use the Bellman equation, which is again just copied and pasted from that prior slide. So what did it do? Someone lost a.
That was my game tree I put on and I dropped it and.
It rolled a very long way.
What is that?
It is a hand cream,
Oh, okay.
rolls incredibly well.
You're gonna break some records, I think. We should use that for some kind of physics project. All right, so computing the state value for a particular state. We just want to now use the Bellman equation that says, all right, for the value of this state, we're just gonna find the expected value of this policy, calculating the return, the expected return based on being in this state. How do we expand that? We say, okay, we're gonna take the expected value from the policy of the return at time t+1, the reward at time t+1 that we expect to get. Just the expected reward for that time. We're gonna add to that the discount factor times the reward that we expect from there. And that's a way of approximating the value of this state. So if we have an understanding of the value of each of these states, we can then back propagate that to here based on the value of the discount factor. So what is the time value of winning now versus in the future? What is the time value of money, whatever it is that you're doing? Breaking this down, we have to sum over many, many components. So this is really just, I think we've basically already seen this, but we're saying sum over all of the actions that we can take from the state based on this policy, the chance that we take this state, probably we take this action given that we're in the state. So we sum all of those, multiply that by the sum over all possible successor states, the sum of all possible rewards for being in that successor state. So we're gonna really combine those together. Each successor state is gonna have a particular reward associated with it. So we just combine them together like that, taking the probability of being in that successor state and getting that reward, given that we were in this state and took this action. And we multiply that by the reward that we got from transitioning from state S to state S prime. We add to that the discount factor, the fact that whatever value we're in this new state, we need to multiply it by that discount rate to say that we're in this state, when we get here, it's sometime in the future. Which means that the value of this needs to be back propagated with that discount factor to say, it's not yet, it's one turn from now. One time step from now. So you multiply this whole thing by that discount factor, by the expected value in the policy of the return from that state on. So we're defining the return from this state in terms of the returns from all possible successor states. Think of this like, I can make some number of decisions from here. There are gonna be some consequences, potential consequences of what I do from here based on some probabilities. I don't know the value of these, I know the value of each of these states, but I don't know the associated probability. I can backtrack all of this to here, saying, if I were to shout an obscene profanity right now, there's a chance that all of you would say nothing, and there's a chance that someone would report me. Should I yell that profanity or not? If I knew what the probability was, I could do some kind of calculation to determine whether it was worth the reward that I think that I get for shouting some profanity. Maybe I'm just so frustrated at the moment that I get some, it's like I'm letting something out. Great. But there's that probability that someone says, you know, that's pretty inappropriate. That's not very professional. I'm going to report them. And I'd have to take that into consideration. So now I can decide based on the policy that I'm using whether I should do that or not. There will be an optimal policy, whether it's worth the chance. So to do that, we go through a process called iterative policy evaluation. This is the most important aspect of the dynamic programming approach, is this concept of iterative policy evaluation. We are going to figure out the value of an entire policy by analyzing all of these successor states, basically, and say, if I keep my decision process the same, what is the expected value of playing this game or being in this situation? If you're an agent of any kind, doing whatever it is this agent is supposed to do. We don't want to solve the linear systems. Instead, we're going to use iterative methods to converge on the real values. So instead of solving 10,000 equations and 10,000 unknowns, we're going to iterate and get there and approximate the result. So we get an expected update by using the Bellman equation. And we can now say, all right, we're going to analyze, backpropagate, analyze, backpropagate, analyze, backpropagate. And as we do this process of kind of level by level, looking at the Bellman optimality equation, we can eventually, via some process of this, converge on the actual values of each of these states. And based on the policy of how likely we are to choose each action, we come up with the value of the initial state. That tells us now the value of that policy. So you can imagine, here are all of the ways to win and or lose tic-tac-toe. Here are all of the states that lead to all of those winnings and losings of tic-tac-toe. Here are all of these states that lead up to winning and losing tic-tac-toe, etc. Here are all the states that lead to that, and eventually you get to the very top, where you haven't made a decision yet. If we play with a random policy, how likely is it that you win the game? We could use the Bellman optimality equation and at each one of these, analyze the value of each one of these states. We would backpropagate this to here, this to here, this to here, this to here. Then we would backpropagate this to here, this to here, this to here, this to here, via some repeated sequence of analyzing all the way up to the top. And we would get a sense of, based on this policy, how good is it to start this game? Does that make sense? Lots of dead stares.
Just processing. Bring as a buffer overflow.
Yeah. So going back to the concept of the Bellman optimality equation, we're talking about this in terms of understanding the value of a particular state. Now we want to understand the value of an entire policy. The fact that every time you play tic-tac-toe, you start at an empty board. And anytime we can make a decision, we're just going to do it random. To figure out the value of this, it's going to be, if we do it random, we're going to figure out the value based on these. These values are going to be based on these. These values are going to be based on these, based on these, based on these. Eventually the game ends. We can backpropagate the value of taking these states to here, these states to here, and we just kind of slowly backpropagate until we get a value that is probably something like, if you're playing randomly, you win the game 1% of the time. Because random is not very good. But it gives you a way to come up with the value of a policy. If you were to play in a more intelligent way, the value of that policy would be higher. If you were to actively sabotage yourself and try to lose the game, then you would probably come up with a value really close to 0. So iterative policy evaluation is just going to iterate through all of this, come up with values. And you see that you're going to have to iterate this an arbitrary number of times in order to get this to backpropagate here, this to backpropagate here, this to backpropagate here. But once it backpropagates, this changes the values of here. So it's a continuous process that you have to go through until you make little enough change that you call it, I've converged. Let's give you an example of this, because I think that it'll make a little bit more sense with an example and also an algorithm. So here's an algorithm for iterative policy evaluation. We're going to terminate when the changes that we make to this are small enough that we basically say further changes are irrelevant. Don't change what we how we value these states by a sufficient enough point that it's going to change what we want to do. So the example that I want to use is this concept that we're going to call grid world. The goal of grid world is to get either here or here. The actions that this agent can take, the agent is going to end up in one of these states initially, and we want to minimize the number of actions that it takes to get to one of these check marks. You can imagine now that we start with a random policy. What a random policy means is that we are going to just, wherever it is that we are, there is a 25% chance that we go in any one of these directions. Every time we make an action, we get a reward of -1. The goal is to maximize the reward that we get, and we will do so if we just beeline it to one of these check marks, whichever one happens to be closer. This initial policy of randomly walking, randomly choosing a direction and going in that direction, is that going to be optimal? No. But we could figure out if there was an equal chance to end up at any one of these, or to start the episode at any one of these positions, we could figure out how good is it to be in each one of these states. According to this policy, how many moves would it take on average to get from 3 to a check mark? How many moves on average would it take to get from 9 to a check mark? According to that policy of moving randomly. Obviously, the optimal policy here would be to go 1, 2, 3, or 1, 2, 3. So you could get there in 3 moves. But if you were using this policy, how many moves would it take? Well, some episodes are going to be infinitely long. If we wanted to start in 9, it could be that there is some episode where we go 9 to 10 to 6 to 5 to 9 to 10 to 6 to 5 to 9 to 10 to 6 to 5. There's no guarantee that that ever terminates. But eventually, enough of the possible episodes would have terminated that it doesn't matter that some episodes are still running after 1,000,000 iterations, 1,000,000 steps. So we're going to try to figure out the value of being in each one of these states by simulating a step into the future. And then simulating another step into the future. And simulating another step into the future. So how does it work? We just start by saying the value of each of these states is 0. To the best of our approximation, we don't know anything. So this was the state that we want to get to. This was the state that we wanted to get to. At time step number 1, if we were in this state, we could have moved here and terminated the episode. We could have moved here. We could have bumped against this wall and stayed, or we could have moved here. So with probability 1/4, we terminate the episode with score -1. With probability 1/4, we're over here. Probability 1/4, we're down here. Probability 1/4, we're still here. Make sense? If we were to sum up the reward that we got from all of that times the probability that we took that action, we would have 0.25, the chance that we moved left, times the -1 reward that we got for the move that we took. Plus, we would actually have 3 more copies of this. Because no matter what you do, you've taken one action. One of those terminated the episode, and we can stop thinking about it moving forward, but the rest of them are continuing. So that's why this box gets a score of -1. We have, with 25% chance, we get a score of -1. We have 3 more copies of that. What is 0.25 times -1? Plus 0.25 times -1, plus 0.25 times -1, plus 0.25 times -1? -1, which is why that goes in this box. Same thing for everything else, except for the 2 where if you start already at the final, then there's no action to take. The episode's already over. There are no further actions to take, so the reward is 0. But you start anywhere else, no matter what move you take, you end up somewhere else, or back in the same place. Questions on how we calculated this value for one step? All right, now let's assume that we are here again on the second move. So basically, after one move, we find ourselves here. Doesn't matter how we got here. The Markov process, that Markov holds. So we're here. With 25% chance, we're going to bump against this wall and stay here. With 25% chance, we're going to move here. With 25% chance, we're going to move here. With 25% chance, we're going to move here. But now, instead of taking just the -1, we now have to consider where we end up. Here we end up with a value of 0. Here we end up with a value of -1, -1, and -1. So we could construct this to say, well, with 25% chance, we're going to take one action to get to somewhere that has a value of 0. But now we need to consider what happens if we go here. We're going to get a reward of -1 when we get there. So we now need to consider there's a 25% chance that we take an action and end up in a state with a value of -1. We're going to get 3 more copies of that. You take the average of those, since they're equally likely, and you end up with -1.7. It's really -1.6666, but we're rounding to -1.7. Because one of those episodes from the prior time terminated. So we don't have to consider what happens from there. But we're doing this iteratively, step by step. We're looking at the value of these states update based on each iteration. We're calculating the value of being there, looking at every possible successor state, backtracking that to the new value of this state, and then iterating. So we see that at time k equals 2, anything that's adjacent to one of the end states has a better value than ones that are not adjacent. In 2 steps from anywhere else, you haven't had any episodes able to terminate. If you start over here and we're looking 2 steps ahead, none of those have had a chance to terminate. Nothing here, it took 2 moves to get there, but we're still only looking 2 moves ahead. So it's going to start to get better from there. At time k equals 3, it's starting to look better, and eventually k equals infinity, we start to converge on these values. That gives us the real estimated, the real expected number of steps that it takes for that process to terminate. So the answer to, if you use a policy from 6, how many steps does it take on average to hit either here or here? The answer is 20. And we got there via approximation and iteration. We used the Bellman optimality equation to look at what is the value of every successive action, back propagate that to the value of this state, then move on and do it again, then move on and do it again, then move on and do it again, and eventually it converges to these values. Which is really interesting to think about and see. Does everyone buy that? Do you think that if you simulated from box number 1 with a random policy, you're either going to move up, down, left, or right with equal probability, the average number of iterations it would take to reach one of these checkmark boxes is 14? If you don't believe me, write a script. Play it out a million times and see what the average is. It's going to be very close to -14 or 14 total steps. If you start in 3, it's going to be really close to 22 steps. So this is the concept of policy evaluation. We can see that if we use the policy that is randomly moving, we get a sense of how good it is to be in every single state in this really simple game. How are we doing? Does that make sense? do we see how it is an application of this algorithm and or an application of this idea? This is really just playing out what that math was describing. We're gonna look at every possible successor state. We're gonna look at the value ending up in those successor states. We're gonna use that information to update the value of this state. We do that for every state. And then we do it again, based on the new values of those states. And that gives us new values of each of those states. And then we do it again, and we update the values of each of those states based on the old values of those states. We do it again and again and again and again and again until it terminates. Once it terminates, we have the actual values. And of course, this won't actually terminate to these values because K has to be infinity, but we could say, once we change each of these values by less than 0.0001, terminate, stop. We've gotten close enough to the real values that we're done. The number of iterations it would take to reach that value would depend on your margin of error. You have a high margin of error, you'll terminate faster. Low margin of error, you'll need to spin for longer, but your results will be more accurate. Four. That took a little bit longer than I thought to explain. How are we doing? Any specific questions about this? How do we feel about understanding what this process is going through? Maybe show of thumbs. Understand it, kind of understand it. All right,
I have a vague idea of what's going on.
excellent. Yeah,
So I'm just looking at all the states. And then there's when it updates, when we go from K1 to K2, we update. Update the boxes that are exactly one space away from a end terminating point as the same value.
yeah. So maybe the better way to just distribute this -1 and have it out, because no matter what action you take from here, you're getting a -1 from the action that you had to take. For every episode that hasn't terminated, make another move. So getting from here, we just say, all right, with 25% chance we get here, 25% chance we get here, 25% chance we get here, and 25% chance we get here. So let's actually write it down. We get 0.25 times 0 as one of them. 0.25 times -1. 0.25 times -1. And 0.25 times -1. And at the end of this, all of these did one transition, so we're going to subtract 1. So the value of this, and this should get you to -0.7 or -0.6666. I guess that's 75. You have 1, 2, 3 chance to get to -1 and 1 chance to get to 0. So this cancels. And this leads you to an average of about -0.7. Then you subtract 1 and get the -1.7, because no matter what you did, you took one move to get there. And that gives you a new approximation for the value of this state. You just take all of those approximations using the old values, update to this table, then loop around, and now you're going to use this table going through exactly that same math, except that the values that you use here, 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 and here are going to come from the last iteration of the table. So when you do this from k = 1 to k = 2, you're referring to the k = 1 table. When you're going from k = 2 to k = 3, you're going to use the k = 2 table. When you go from k = 3 to k = 4, you're going to use the k = 3 table. And each time you're building a new table based on this. And by the time this algorithm terminates, we have the actual real values for all episodes that terminate after that many steps. So if we went up to k = 10,000, we'd have the value of all episodes that terminate within 10,000 iterations. All episodes that terminate within however long we want to go out. eventually, if we have said K equals 10 million. That 10 million in first iteration is gonna change the table, the values in the table by so little. That we can say we're basically done. It's not changing enough for us to need to update this. We can terminate and say, this is a very close approximation to if we continue this process forever. And what it will converge to is the number of steps it will take for it to terminate the game. Win the game, as you might say. Further questions? So this is policy evaluations, answering the question, how good is this policy? It turns out that we can find that this policy has this result. But what are the actual best moves? Does anyone want to, if you were designing an agent to play this, what would the actual values of each of these states be? If you could customize the policy. From box 1, you would just want to move left with probability 1. That is the part of the policy you would want from that state. You would never want to move to 5. You would never want to move to 2. You'd never want to bump into this wall. You just always want to go left. How about from position 2? Where would you want to go?
Left.
Just left? Always? How about from position 6?
The same distance.
Up, left, down, or so.
Yeah, it doesn't really matter. There's a way to get to a terminating to either check mark with 3 steps. So the value of this state should really be -1, saying that if we have this policy, you're always 1 step away from the end of the game. From here, this value should be -2, saying that if we follow this policy, we're always going to get here in exactly 2 steps. So how do we turn this arbitrary policy, this random policy, into an intelligent policy? It turns out that when this terminates like this, what you can do is say, all right, we're in the box that is -14. If I move left, I get value 0. If I move right, I get value -20. If I move up, I get value -14. If I move down, I get value -18. The maximum of all of those is 0. Instead of probabilistically making one of these actions, instead take the maximum the action that maximizes the return. 0 is better than everything else, so instead of doing anything from this state, just go left. From -20, you can choose -14, -20, -22, or -20. The maximum of those is -14. So instead of randomly making a choice from this state, we're going to always move left. So we can turn this termination into a new policy. In fact, with a single step, it is the optimal policy. If we let K go forever, or close to forever, then in a single step, we just get to the best policy that exists for this game. So we call that policy improvement. And that's exactly what it says here. We're going to say that instead of using this policy, we now can look at this terminated value and say instead of doing this, we're instead just going to go to the action that maximizes the expected return. So you turn that policy into this. And this policy is guaranteed to be an improvement on that policy. It's going to get a better return from every single state than the policy you started with. This allows us to turn something like this, a policy that does this, into a policy that does this. And honestly, we should be able to that right?
No, not quite, not
this one.
left on, yeah.
That one is fine.
Yeah.
Yeah. So it's slightly wrong.
So when we look at 6, like, the choice is always to go to the -18. Like you would never go to the -1 if you're following that policy. Even though we said that all were valid 3 steps, so are we talking about them? But then they cumulative. Yeah.
Yeah, so if we're going from something like here. It says it doesn't matter which way we go. We go down, but now we can only move down or right. We can't move back left. So from here, if we go down, it's gonna take 1, 2, 3, or 1, 2, 3. Or 1, 2, 3, or 1, 2, 3. The only ways to go from this policy are the optimal paths that lead to the fastest way to get to one of those ending states.
Why differentiate between, well, but. Those are all optimal paths, but they have different values.
They do have different values than this.
Yeah.
But if we were to go through policy evaluation of this. This would terminate to -1, -2, -3. -1, -2, -3, -2, -2, -3, -3, -1, -3. -2, -1. That would be the policy evaluation that this would terminate at, which is a significant improvement over this. And if you evaluated this and then went through the policy improvement idea, you would find that no matter what you do, you can't improve on this. This is the optimal policy for this game. So the idea is we're going to iterate between evaluation, improvement, evaluation, improvement, evaluation, improvement, until evaluation says you can't improve.
Is that center bottom right cube supposed to be -3 or is it supposed to be -2? Like,
Oh yeah, it should be -2, shouldn't it? Yeah, it should be,
all threes in the middle and then.
yeah. It should be, this is a mirror, everything should be the same across each of those values from that point. Thank you. How are we doing? Does that make sense? We look really excited to get out of here. We're definitely gonna stop here for the day, but we'll pick this back up next week. Would people prefer to do kind of a half and half on Monday and Wednesday where you do, I meet with half the teams on Monday and half the teams on Wednesday, and we have half as long of a lecture?
Do a good stuff.
Or would we rather have a longer period of time to meet and work, and then a longer lecture on the other day?
Yeah, I can do that.
So you want
I-
Lecture on one day versus
It's
split?
not.
Yeah.
I feel like it's just such a long lecture, it's hard to stay
Yeah.
focused and engaged
Yeah.
the whole time.
What would help people for that? Is that more breaks? Is that just randomly in the middle of lecture, no one judges anyone if they just stand up and start doing jumping jacks? What would help? Because I do think that having the time to work together on one of the class periods for a longer period of time leads to more productivity than where are we? Everyone summarize where we are. Now transition to making progress together. If you can minimize the amount of time that it takes to do that, there are fewer disruptions that lead to more productivity.
I think we can start by actually taking the 2 breaks you gave us instead of just 1.
Yeah, people need to advocate for that second break.
I've seen in other classes where like there was, for example, 1 lab day and then 2 like lecture days that were.
Yeah, spread out more.
Like 2
That's-
1-hour lectures on
Yeah,
and then like a 2-hour lab.
So good push.
That might also not be a bad idea.
that would work.
It-
The struggle that I have with that is it overlaps more potential
That's because
courses
you're
that students can take. So if I do a Monday, Wednesday afternoon like this, then. Like what would work better for other people's schedules? To have you here for an additional afternoon? But do something that was more like an hour and 15 minutes. Twice, and then have 1 longer workday. Would we rather be here Monday, Wednesday, Friday, or Monday, Tuesday, Wednesday, or Monday, Tuesday, Thursday, something like that, and spread out the lecture among 2 days? Would it be better to have that, in your opinion, or would it be better
I
to?
like the idea of doing half and half on both days. So like in the morning, when we first get here, we can do like an hour worth of talking and doing our project, and then the other hour we can work on our shorter to lecture.
I mean, like,
We should honestly just take a vote. As to who would prefer what.
I know
Yeah.
you were talking about how it does make it somewhat more difficult to like
I
synchronize.
think it's as well.
But I also feel like
For a set amount of time.
Yeah,
we should be,
I like
we
that a
should
lot.
be talking enough outside of class. That really by the time we come into this room, we should already
Ready to go.
mostly, not completely synchronized, but just be kind of like. We shouldn't be needing to spend like 10-20 minutes catching each other up, we should be like. Here's what I did last night, you know?
Right,
There's a game plan already in place.
yeah. Who spends the first 10 or 20 minutes catching up at the start of a class? A reasonable number of people. So I think that in an ideal world, that would be great, if we could all agree that we're going to communicate ahead of a class period. That we're gonna hit the ground running from minute one, we're all gonna know where everyone is at that time. Then maybe that becomes a better idea.
Well, the standard like CS course load, at least from my experience, has been 3 classes a quarter. So I feel like splitting the lecture up into 2 regular class size days would not be bad. Even if they started at 2. Or like a little bit later. I personally don't like being in this building until 5 o'clock, so I still have to go back to Cheney. But,
Yeah, if you stay until 5, then you get traffic going, right? It's not
Yeah.
too bad from here going west, it's worse going east.
well, and the main bus to the campus only leaves every 30 minutes. Yeah, so there's like 8 minutes until it leaves next and it's all the way across the bridge, so. So. if I
Hey, go
don't-
get your bus.
So. I think last quarter it started arriving